All right, let's take a look at what we've got here. So in this case, we have our initial starting point for our vector at the point -3, -7. We have our kind of concluding value, our concluding point here at 2, 5. What is our vector that we get from this? 5, 12. So you could either write this in our component form of 5, 12. How far have we moved in the x direction? To go from -3 to 2, we have to move by 5. How far have we moved in the y direction? Well, from -7 to 5, we have to have moved by 12. You could also write this as 5i plus 12j. That would also be totally fine. Either way, perfectly acceptable. In order to find, now I don't think I wrote this notation last time, but I'll put it up now just so that we see it. The magnitude of this vector v, which is the same thing as finding that value of r. What do we have to do in order to find the magnitude? Yeah, or the square root of, I might describe it as like x squared plus y squared, but certainly that also works, which in this case is going to give us 13. 5 squared plus 12 squared, take the square root of that, you should get 13, or the square root of 169, same thing. All right, what equations does that allow me to set up in order to find theta? Yeah, cosine of theta is x over r, or 5 over 13, and sine of theta is 12 over 13. Do we know the theta on the unit circle? That's going to give us an x value of 5 over 13 and a y value of 12 over 13. No. And so we are going to need to use our inverse trig statements in order to figure this one out. As far as inverse trig, we need to know what quadrant we are pointing towards. What quadrant does our vector point us towards? This is a quadrant 1 pointing vector. Positive x, positive y. And so if we're looking for a quadrant 1 theta, does it matter which trig function we use? Do we have to use sine or cosine, or can we choose either? We can do either because both of our inverse trig statements will spit us out in quadrant 1. If this were a quadrant 2 vector, which one would we have to use? We would, for quadrant 2, cosine for quadrant 2. And then for quadrant 4, we would have to use sine. And then what was that trick that we looked at on Friday to get us into quadrant 3? How do I get to quadrant 3 from something that I can actually compute very nicely and easily? Add pi to an angle from which quadrant? Yeah, from the first quadrant. So if we find a first quadrant angle and then add pi to it, that will take us to quadrant 3. In this case, quadrant 1, we can use either, does not matter. And so maybe we'll say something along the lines of theta equals cosine inverse of 5 over 13, or you could say sine inverse of 12 over 13. Either way is, of course, perfectly acceptable. So this is our R, and this is our theta. Questions here from our bell work? Yeah, Simran. So wait, what's the question? You just write the inverse trig statement that goes along with the statement that you have. So for instance, saying that cosine of theta equals 5/13 is equivalent to saying that theta is equal to cosine inverse of 5/13 if what we are looking at is a quadrant 1 angle. Now, if it's not, then we run into issues and we shouldn't be using that cosine inverse statement. Instead, we'd probably be needing to use the sine inverse statement. Other questions here? Hopefully this is very, very similar to what we did for 6-1. Hopefully it's very, very similar to what we did for 6-2, right? You're just finding R, finding theta. Before in 6-1, we were writing it as R comma theta, like a point. In 6-2, we were writing it as RCIS of theta as a polar form complex number. And now we don't have a form for it. We're just saying what R is, and we're just saying what theta is. So same information, just slightly different presentations each way, slightly different meanings alongside each one as well. All right, a couple of things to mention before we continue on today is you either probably heard from another class or maybe were able to ascertain from the fact that we had a bell work. I am pushing the quiz that was supposed to be today back a day. So it will instead be tomorrow during class. Same with the classwork. I have pushed that back a day as well. So if you did not, remember to do that over this weekend. Make sure that you take a look at it before tonight, where it will be due. So do tonight instead, and then quiz tomorrow. Test still on Friday. My game plan is to finish 6-1, not 6-1, we're done with 6-1, 6-3 today, to be done with Unit 6 with all the new information by the end of the day today. Quiz tomorrow, review day, Wednesday, Thursday, test on Friday. That's the game plan. All right, so a couple of reminders from Friday. We were taking a look at vectors, kind of our introduction into vectors. And my claim was that really vectors are just two-dimensional numbers. They are not, or not even two-dimensional numbers. They're just numbers, right? You can think of them in 1 dimension. You can think of them in 2. That's fine. We scaled them up to be thought of in terms of 2 dimensions. That was kind of the bulk of the end of what we were doing on Friday. Today we're going to be looking at, we're going to start with some operations that we can do with vectors, how we can combine and create various new vectors. We already looked at this in the 1-dimensional case. For instance, if I say that I have my vector that is 3, which we know starts at whatever the start point is and goes to the right by 3, what did I have to do to find 2 times the scalar 2 times that vector? What does this 2 do to my original vector? It doubles it. It doubles the length of the vector. It doubles the magnitude. It also doubles the, kind of the component that tells us this. In the case of a one-dimensional vector, you don't really see this, but certainly we will see that this has a very specific kind of effect here momentarily. But for our purposes, it doubles the length of our vector. We saw that the -1, so if I take negative v, what does this do to my vector? It takes it to the opposite side, so same length, different direction, in particular the opposite direction. So we go out the same distance, just in the other way, 180-degree rotation. And the way we add vectors, for instance, if I wanted to take, let's say that u is equal to -2, and we want to do u, we'll do -v plus u. Then the very, very simple thing that we can think of for following these instructions is first we follow v. So we take v out to -3, and from where v ends, we then follow u. So we go out to the left by 3, and then from this point, we travel an additional 2 to the left for a final vector that captures all of our change, traveling, in this case, 5 to the left. Which algebraically, very, very simply found just by adding these component movements. We're going to find that the ideas in 2 dimensions are pretty much the same as what we see in 1 dimension. It's actually fairly straightforward the way that we combine and get these kind of new vectors here. So we are in, of course, the XY plane now. And we'll say that we are looking at relatively small. We'll say that the vector v is equal to the vector 3, 1. And so we go over 3 up by 1. Something like this. Vector b. But that's going to get messy, so we're going to leave that off, actually. We could think of very easily figuring out what's going on with 2v. What did we say multiplying by a scalar does to the length of our vector? It's going to double the vector, so whatever instructions we followed before, we are just going to follow them again. As far as thinking about what this is going to do to our components, very, very simply, doubling the length of the vector is what we get when we just double both the x and the y components. And so this new vector that we would end up with is going to have the same direction as the original, but it will be twice as long. This would be our vector 2v. So exact same idea as before. We are doubling the length of the arrow, doubling the magnitude. The way that we can accomplish this is we can double the x change, double the y change in location in order to arrive at this kind of final vector. Could also think of adding it to itself, but that idea is one that will come here momentarily. As far as addition is also going to work in a way that is very similar. So v is equal to 3, 1. Let's maybe set w equal to the vector 1, 3. With our one-dimensional case, we found that we could arrive at the resultant vector by first following the instructions of v. So if I want to know what v plus w is, that first we could follow the instructions for v, then we could follow the instructions for w. If I first followed the instructions to v, then I'm going to be taken to this point here. If I then follow the instructions for w, which is going to look like this vector here. So first following v, then following w. Then we are going to end up at our final destination that we see here. Ultimately, with vectors, we are trying to figure out what the overall kind of change in x, change in y was. We could think of traveling by our initial change in x and our initial change in y, and then our second change in x and our second change in y. The simple short answer is that we're going to end up arriving at the sum of these. And where it connects is going to be from the start of our first vector to the end of our final vector will give us the new sum vector that we can arrive at algebraically very simply by adding the x components and adding the y components. Now, there is a way to think about geometrically adjusting for subtraction in a way that is fundamentally different than how we do addition. I think that having two different methodologies, one that we follow for addition, one that we follow for subtraction, is very redundant. I think an easier way to conceptualize the way we might subtract vectors, for instance, if I wanted to take v minus w, algebraically, this is going to be fairly straightforward. It'll be exactly what you suspect. You subtract the x values, you subtract the y values. That's not too bad. Geometrically, the way I would recommend thinking about this is as taking v plus negative w, where we know that taking the negative of our vector simply reverses its direction. So if w is 1, 3, we said the vector that's going to look like this. Then when I take the negative of this particular vector, then the only thing that changes here is rather than my arrow pointing up and to the right, my arrow will instead point down and to the left, simply rotating it 180 degrees. And exact same thing, we want to take our kind of new negative w vector, we would be adding it to where v kind of leads off, something like what we see here. And our resultant vector would be exactly what you get from the start of v to the end, in this case, of negative w. We're mostly going to focus on the algebraic, which is, again, the one that's fairly straightforward. You add the x's, you add the y's, multiply the x's, multiply with the y's by, what we see here. But I did want you all to kind of see that there is some geometry underlying what we are doing as well. All right, let's take a look at example 3 here. In this case, we are given two vectors, vector v defined as said and vector w as well. We'll start with A. We are trying to find v plus w. Very, very simply, we are taking the sum in the x direction. So this is 3 plus, in this case, -1. And the sum in the y direction, in this case, 2 plus 7. To arrive at our new vector, you could either write this in the ij form or in the component form. We'll say that this is the vector 2, 9. Again, in terms of the geometry, which I will continue to harp on at least for a little bit. If we are thinking about the vector 3, 2, vector that goes over 3 up 2 is going to look something like what we see here. The vector that is going to go back 1 and up 7 is going to look like this. And if I want to add them, we are taking where this vector leads off and attaching it to the start of our second vector, exactly as we see here. And if we ask what is the net change in x, what is the net change in y? Well, from our first vector, we slid over 3. From our second vector, we slid back 1. And from our first vector, we slid up 2. And from our second, we slid up 7. We end up with exactly what we calculated algebraically, that this would be the vector 2, 9. Questions with our vector operations here, scalar multiplication and the addition or subtraction of our vectors.
Could you redo the part where you, before you drag them over, to form the V?
Sure. So looking at like this. So for the vector -1, 7, -I plus 7j, backwards by 1 in the x direction, and then up 7 in the y. And then we were just saying, if I'm doing v plus w, we first go out by v, we travel by v, and then from there, wherever we stop, we're then going to continue by w, which takes us like what we see here. Which matches what we found algebraically, that this is 2, 9. And we're able to move our vectors around like that because do the vectors care where they start and stop? No, they just care about the instructions that they follow. So you can follow those instructions from any start point. That's totally fine, which is why we are able to freely move our vectors around like this in order to set up these kind of geometric ways of adding our vectors. And we can really, really think about them as starting from where the last one stopped. You could continue that idea if we wanted to add more vectors. Then you would just continue picking up where the last one left off over and over and over again. And then your final result would be start of your first vector to the end of your last vector. But again, we're going to mostly be focusing on the algebraic, which is just the very, you add the x's, you add the y's. Let's take a stab at B and C. We'll take maybe 5 minutes. My advice for when we have this kind of scalar modification on a vector is to treat that like it's its own vector to find what that is equal to, and then worry about the addition. So kind of break this apart into 2 different steps. So my first step for B would be to figure out, okay, what is negative 2w? And then from there, do the addition. Yeah, you can multiply both. Kind of, if that's how you want to think about it. Yeah, that's not a bad way to think about it, of distributing the 2 in. Yeah. So it's not different if we're thinking about just like the path that we follow. Our final answer is just going to be from start to end, what path do we take? So notice that the start to end for both paths is the same, and the way we need to describe it is just the faster way to do it. So you could think about like the difference between, this is actually a fairly deep question. You can think about the difference between this set of directions and this as being the difference between writing our vector like this and then simplifying it to 2, 9. When we simplify it, we lose the individual steps that we took along the way. But before it's simplified, this actually tells us a much more kind of vivid, detailed picture of what we're actually following.
Okay, so they are the same.
They're the same thing. Yeah, it's the same thing. And we are just, the red is going to be your final answer because that's like ultimately the steps that you.
Also for the first arrow,
yeah.
The first black arrow, why is it angled upwards?
3 plus, so 3, 2 is going to be positive 3, positive 2. Yes. Yeah.
Basically, it's just like bullet points, except you connect them
With an arrow. Yeah. Yeah, these are basically, they're basically points. Yeah. Three minus negative 2 can be 5. That's why minus and negative gives you a positive. But yeah, otherwise it's yep, otherwise it's yep, that looks good. You need to make sure that you're multiplying the components of W by -2, not the Y components by -2. So for instance, this -2 needs to be here, and it needs to be here. Yeah, exactly. Because that's part of V, which is not being modified by components. Yep, those look good. Those look great. When we're doing, make sure you're doing the negative here. Yeah, the negative 2. When I do -2 times the x component, what's that? It'll be plus, yeah, so this would be 5 instead. It would be 3 minus -2. Yeah. Yeah, what you have here is perfect. It's just 3 minus -2. So what I would do for graphics is I would do the negative version of this, which would take this vector that you have here and it would flip it backwards, send it backwards, and then I would line it out, and that's how you're going to get your 5, -12. In that range. Now, this is actually moving in the positive x direction, so it's actually going to be angled this way because it's -2 to go back to up. So it'd be angled the other way, but then you would flip it because it's negative, so negative tells us that we switch directions, and then you would line it up and that would get the vector that you're in. There is like a separate method, it's called like the parallelogram method for subtracting them, and I just like that. I do not know it, because again, like why do that when you can just multiply by -1, and that's just easy. Yeah. Grab a hot bus again. All right, let's take a look here. So first thing that I would do here is I would start by finding what -2w is, and we're doing then v plus -2w. I saw a lot of people found 2w instead and then subtracted the x components and subtracted the y components. That's also fine. That's perfectly acceptable. You'll get the exact same thing. But for -2w, I found that this was the vector, +2, -14. And so adding my x components here, I found that this was a result of 5 and -12 for my vector. Likewise here, 2v is going to be the vector 6, 4, and adding it with w is going to give me adding my x components, I get 5 in the x direction. Adding my y components, I get 11 in the y direction. All right, questions with our kind of basic vector operations here. All right. Next thing that we are going to be looking at is actually something that we have addressed very briefly. We've already looked at a couple examples of these. When we're talking about vectors, we normally refer to vectors again in terms of their direction and magnitude. But there are some vectors, and there are some instances where a vector with a large magnitude or even like a small magnitude can kind of interfere with figuring out the directional information of our vector. And so there are going to be some instances where we want to work with a modified version of our vector that essentially is going to only encode for the directional information, not really carrying with it any kind of magnitude information. The two vectors that we have already seen that do this were our vectors I and j, which, again, we're not really trying to contribute anything magnitude-wise, but we're instead working as just kind of telling us that, hey, if we're going in the I direction, then we're following the X direction, and if we're in the J direction, then we are following the Y direction. These vectors, which are kind of have the magnitude removed from them, that have been stripped of their magnitude, are called unit vectors. And kind of an easy way that we can think of defining unit vectors, these are going to be vectors that have a magnitude of 1. Now, if we're thinking about how we might strip away that magnitude, for instance, let's say we have a vector that has a magnitude of 3. What would I need to do to this vector in order to, first of all, make sure I'm not changing the direction? So whatever operation that we do to this, we need to make sure that it doesn't change the way it's facing, but also that reduces the magnitude from a magnitude of 3 down to a magnitude of 1. What could I do here? How can I modify this original vector v? Yeah, absolutely. If I had a magnitude of 3 and we want a magnitude that is a third as long, then we just need to either multiply by 1/3 or, totally fine to think about it this way as well, divide by 3. We divide out the magnitude and we are left with a vector that just tells us something about the direction. If we wanted to kind of generalize this, then we might say something along the lines of we take our vector and we divide it by its magnitude, written like this. But again, this magnitude that I have written is really just a fancy way of writing r, right? We take our vector, we divide both the x and the y component by this value of r. So for instance, taking a look at number 4, trying to figure out the unit vectors that correspond with the vectors that we are given. This is as simple as finding r and then dividing our vectors by r. So in this case, the magnitude of our vector v is the square root of 8 squared plus negative 15 squared. 64 plus 225 is 289. Square root of 289 is 17. And so our unit vector is going to be, in this case, 8 over 17 and negative 15 over 17. Not changing the direction, just dividing, scaling back both the x and the y value by this factor of 17. I just used a little arrow to denote that what we're talking about is a vector. Yeah. So you'll notice that we have them for each of our like i's and j's as well. And that's just to say that we're talking about the vector v or the vector I, rather than like the imaginary number I or something else. Technically, you'll see this also written with like a bold script. So if you see like a bold script V or like a bold script W, that's also referring to a vector. But I think that's stupid because one, you can't write that in notes. And two, it's like very not clear why that would be referring to a vector, it being bolded. Whereas like, oh, there's an arrow here, we're probably talking about a vector, I think makes a lot of sense. But who am I to argue with mathematicians who are a lot smarter than I am and who came before and said, all right, we're just going to bold our vectors because that makes sense. All right, take a stab at B and C. Figure out the magnitude, dividing each of your components by the magnitude to get your unit vector. You'll notice I'm writing these in the component form. There's absolutely nothing wrong as well with writing this as like 8 over 17i minus 15 over 17j. That's also perfectly fine. I'm just defaulting to the component form. But they're interchangeable. They're the same. Yeah. It's a good place. Yeah, that looks good. I mean, it'll depend on the positive versus negative of the x and y. So if you have a positive x change, a positive y change, it's going to be some kind of
quadrant 1 angle is going to be pointing towards quadrant 1. Negative x plus y will point towards quadrant 2. So.
But otherwise, looks good. Yeah.
Yep, perfect.
It's really, really simple. Really, really nice.
Yep.
Hmm.
Yep, those are great.
All right, let's take a look at our solutions here for example 4. What was the magnitude that we found for W? That was 5. Square root of -3 squared plus 4 squared, you should get 5 there. And so our unit vector is going to be, and again, you can write this component form or the ij form either way. I'll do the ij form just to showcase it here. -3/5 I plus 4/5 j. All right. Find the magnitude of the vector. So the a squared plus b squared square. Yeah. What did we get for our magnitude for u? 25, which is going to give us -24/25I plus 7/25j. Yeah, you can. It's just the same thing. It's the two different ways of writing the same information. Right. This was our component form, and the one that I used here was our ij form, and both of them are perfectly acceptable. Questions with our unit vector stuff? All right. One kind of new final thing. Example 6 is going to largely be stuff that we've already seen. 6 is taking our theta information and converting it to xy information. We have done that a lot in 6.1 and 6.2. So that one hopefully won't be too bad. Example 5 is going to be a new definition here. You'll notice that with all of our kind of operations so far, we've got scalar multiplication, we've got vector addition. The results of both of these are vectors, right? You multiply 2 by a vector, you get a vector that's twice as long. You add 2 vectors together, you get the vector that is a result of adding each of the individual components. Regardless, what we don't have up here is a way to multiply 2 vectors together. And you could certainly maybe conjure up some kind of way to do that, of maybe we multiply the x components and multiply the y components. But generally speaking, there isn't a way of just multiplying a vector by a vector to get some larger, smaller, or whatever vector. We just don't really have one, and we're not really going to try to make sense of that. Now, that being said, there are several ways that we can combine vectors. We are going to be looking at one fairly useful instance of this, of a way that we can combine 2 vectors. And that is going to be what is called the dot product of our 2 vectors. Now, at first, and actually not just at first, this is just going to feel pretty weird and enshrined in mystery for the purposes of what we do in here. Although maybe we'll have a challenge set that explores a little bit kind of some of the utility here. But let's say we have our vectors. We had v and w here. So v was 3, 1, and w was 1, 3. Something like this. We looked at adding these 2 vectors together to get 4, 4. But we are going to do what is called taking the dot product of these 2 vectors together. And we're not really going to, for the purposes of this, at very least not in the kind of standard core curriculum that we're going to be assessed on the test, be examining why this exactly works the way it does. But essentially, the dot product is going to give us a number that says something about this angle right here. In some way, somehow, the dot product tells us what's going on about the angle between our 2 vectors. But again, we're not really going to worry too much about why, but that is the connection. This is why it's very useful as just a thing to be able to compute, is it will eventually, with a little bit more work, tell us something that's going on here with this angle between our 2 vectors. So for instance, or we'll just kind of jump into the definition. If we say we have a vector v, which we'll define as a b, and a vector w, which we will define as c, d, then very, very simply, the dot product of those 2 vectors, v dot w, is going to be the product of the x's plus the product of the y's. This is AC plus BD. Now you will notice that this is not a vector. There isn't an x component, there isn't a y component. This is just, it just gives you a scalar. It just gives you some kind of number. And again, my claim is that that number with an alternative way to find the dot product would say something about the angle between these 2 vectors, these vectors v and w. So this is some kind of scalar, but is really the way that we will be combining vectors, is with this dot product. It's the x components multiplied together plus the y components multiplied together. So for instance, if we wanted to take the dot product of v and w, like we have here, v dot w would be Well, A in this case is 3 and 1, so 3 times 1, plus B is 1 times 3. The dot product here would be 6. And as far as we're concerned, that's where we would stop. But again, the kind of next step here would be, oh, well, this actually is telling us something about the about this angle that we have between these two vectors. Now, you kind of need to combine, you don't need to, but what you would do is combine this notion with the idea of unit vectors, because within this 6 is contained both magnitude information and direction information. And so you would need to divide out that magnitude information in order to isolate the directional information. But again, that is beyond the scope of what we'll be doing for the standard part of this class. On a challenge set, that might be a thing that I ask you to do, but not on something like this. This is also the thing that I think was like the most frequently missed on the test that we had over this last year, which I think is just people not learning definitions. So just learn the definitions. The math is not what is going to throw you off. It is just going to be the definitions of understanding what is a unit vector, what is a dot product, what is this that I'm being asked to find. But computationally, fairly straightforward. For instance, let's say we want to take the dot product of the V and W that we see defined here. Very, very simply, we take the product of the x's, 3 times -1, add it with the product of the y's. I get that this has a dot product of 11, which, again, is somewhat meaningless to us, but apparently is saying something about angles. Questions with dot product? All right, take a stab at B and C as well. No, you're not foiling. It's just multiplying the x's, multiplying the y's, and then adding. You can distribute. It shouldn't be a given that we can distribute down more, but you can. I think that might be a thing that you have to prove that you're working in a vector space, but that distribution works. Could be totally wrong. Nope, that looks good. And then if we don't just multiply the x's, multiply the y's, what do we do with these? At the end. So we should just get it. Yeah, so that'll be your first vector. It's the vector negative 2. Okay. And then so you could either distribute, you could do the addition first and then multiply each component by 4, either way.
And then I'm just confused as to what I'm having multiplied.
Will it be this times this and then this?
So taking this dot,
Dot,
whatever, the
that
value of
is.
it, whatever that is. So you want to simplify that, would be my advice, and then over. Positive 18 here, I think is 6, and then this would become positive 3 because it's negative 3. Yep. That's it. That's what you would probably use it for in like an upper level math class, is you would then use it to calculate that. No, you probably already have that information just from the two initial vectors. What you get there is specifically the angle between those two vectors. So it's like how far apart those are rotated. And generally, what you look for is when it's 0, because that means you're at 90 degree, is what is important. It's when the dot product is 0, you get a 90 degree angle. Which lets you use them as basis vectors, and it's a whole other thing, and all that nonsense. All right, let's take a look at what we got here. For B, 2v is really just the vector 6, 4. We're taking this dot, negative 3w, well, that's going to be positive 3 and negative 21 for my x and y respectively. We multiply the x's, multiply the y's, add them together. That's going to be 18 plus negative 84. I get that this is negative 66. That's my dot product here. Negative v is going to be negative 3, negative 2. V plus w is going to be 2, 9. We said that earlier. And then times 4 is going to be 8, 36. Taking the dot product here, this is negative 24 plus negative 72. I get that this is negative 96. Questions with our dot product, other than the obvious, like, what are you talking about that this has anything to do with this? Thank you. Last example, good news is something that we have done a lot. For this final piece, we are trying to figure out what the vector is. So we're trying to figure out that x, y information given an r and a theta. If I start with an r and a theta, if I'm given r and a theta, what equations can I use to find x and y respectively? Perfect. Perfect. So this is just our tool. This is our mechanism that takes our theta information and spits out x, y information. Of course, in the context of this, r is really just our magnitude. You can leave it as r, that's totally fine. But you will also see it written like this. That's just the same thing as r. And so our vector here is going to be that r cosine of theta and r sine of theta. In this case, this will be 6 cosine of 25 degrees and 6 sine of 25 degrees. 25, is that unit circle knowledge? No, so you'd either have to plug it into your calculator or just leave it as is. I would give you something more like what we see with B, where it is unit circle, and so you actually would have to evaluate each of those. In this case, W would be R cosine of theta, R sine of theta, and we can actually evaluate cosine of 5 pi over 6 and sine of 5 pi over 6. This is just going to be negative 4 root 3 and 4. So exactly the same thing that we did in 6.1, exactly the same thing that we did in 6.2, when we were given our polar information, when we knew what r was, when we knew what theta was, when what we wanted to know was what is x, what is y, you are simply r cosine theta, r sine theta in order to figure that out. All right. Questions with